In this video, we're going to specifically think about ionic bonds. So bonds, ionic bonds. So an ionic bond is formed or observed between a metal and a nonmetal. And so what we typically see is that the metal serves as the cation and it donates its electron to the nonmetal or the anion. So the electrons are going to be transferred from the cation to the anion. So if we think about KCl, where potassium is a metal and chlorine is a nonmetal, what do these look like? So if we have potassium, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So in this case, potassium has a single valence electron. If we look at K plus, it is 1s2, 2s2, 2p6, 3s2, 3p6. These 8 electrons here are octet. So now potassium, by losing a single electron, has achieved octet. So when we think about chlorine and chlorine minus, so chlorine has 1s2, 2s2, 2p6, 3s2, 3p5, and Cl minus absorbs a single electron to complete its octet. So we have 1s2, 2s2, 2p6, 3s2, 3p6. So it has also achieved octet. And so we can draw this as K with a single electron plus chlorine with 7 valence electrons to get K plus and Cl with 8. Those are not very big. Hold on. Chlorine with its 8 valence electrons in a bracket with negative charge. So these both have octet, but they are not physically bound together. If they were, and we'll see in other videos, we'll draw a linker between things when they create an actual bond. So ionic compounds and ionic solids. We know they exist, and we're going to think about how they work. So instead of sodium sulfate, which is a little bit more complicated at this juncture, let's look at sodium sulfide. So we have Na2S, where we have 2 sodium ions plus a single sulfur. And we could imagine that both sodiums are going to donate to the sulfur. So we're going to get 2 Na plus S with 8 valence electrons. And it now has a 2 minus charge. So in this case, we have 2 sodiums and a sulfur, all of which have octet. And that's one of the things that's really important and definitely observed in ionic solids. But these don't have a bond. So what we really have is an Na plus, an Na plus, and a sulfur 2 minus with its 8 valence electrons. But if they are not held together, how can we find them without a bond? So we know that sodium chloride and potassium chloride and sodium sulfate all exist. But sodium chloride is an easy example because we use it in cooking and we can see it. You can see solid salt crystals. So we know, both from our current perspective and atomically, that we can create a solid that is 50% sodium and 50% chlorine, and they're interspersed. So we know that if you mix sodium plus half a mole of Cl2 gas, you can get NaCl. And based on the tables we've looked at before, it has a delta H naught F, or the heat of formation, of negative 411 kilojoules per mole. And so based on what we know, what should happen is that sodium should be ionized and chlorine should have an electron affinity. in order to create both Na plus and Cl minus. If we think about these structures in these equations, they don't equal the delta H naught F value. What I'm saying is there's more than just the ionization and the electron affinity occurring. So what accounts for the increased stability of sodium chloride? Because it's not just that sodium is easily ionized and chlorine has a high electron affinity. Those don't account for all of the delta H naught F formation. So it turns out that the ions are stabilized in a repeating lattice, where each positive ion is surrounded by negative ions. So if we look at this and we have positive and negative, so our green are the sodiums, these are our chlorines. So if you look at this, one of the things we can see is that every negative ion is surrounded on three sides by a positive ion. So this is going to be true for all of them, whether in all of the lattices are structurally similar, where we see a positive charge surrounded by negative charges in all three dimensions. So it technically looks a little bit more like a six-sided die. Now, they're not all as neatly packed as this. There are other arrangements that are very stable. If we look at these different lattice energies for a series of chloride ions or chloride compounds, lithium chloride, sodium chloride, potassium chloride, and cesium chloride, the lattice energies change, even though they all have chlorine and they all have an anion with only a +1 charge. So it turns out that the stability of the compound is related to Coulomb's law. Now, Coulomb's law states we have a standard value where the Q1 and Q2 are the charges. So E equals K, Q1, Q2 over R, where Q1 and Q2 are the charges, and R is the radius. So in all of these, the charges are the same, but the radius is going to change because we know as you go down a periodic column, a column in the periodic table, the radii are going to get bigger. So this takes into account that information. So lattice energy becomes less exothermic with increasing radii, less negative. Basically, it's less strong. And it becomes more exothermic with increasing ionic charge. So if we remember Coulomb's law is E equals K, Q1, Q2 over R, where R is the radius, Q1 and Q2 are the charge size. So if we look at two compounds, NaF and calcium oxide, so sodium fluoride, calcium oxide, the radius are 231 and 239 picometers, so very similar. But the lattice energy, this should have a negative charge, goes from negative 910 to negative 3,414. So it is a substantially higher lattice energy that is due to the increasing charge. So the fact that the charges go from +1 -1 to +2 -2 makes a big difference in terms of the lattice energy. So lattice energy is the stabilization of the charges in a 3D solid. So we can look at these compounds and arrange them in terms of increasing lattice energy. So we need to think about these smaller radii and charge difference. So SRO is 2 plus. These are +1 each, +1, +2. So we need to think about which of these are going to be different. So calcium oxide is going to be the largest lattice energy, followed by strontium oxide, followed by KCl, followed by KBr. And so you rank these in terms of the radii and the charges of the ions. So the smaller the radius, the larger the lattice energy is, because E is equal to K, Q1, Q2 over R. So this should say solids, So, some of the things that we know about ionic solids, they're created by organizing charged particles into a stable structure with repeating units. These ions are incapable of conducting electricity in their solid form. However, when they are dissolved in water, they can conduct electricity. And so within the solid, the charges are localized to the specific atoms and cannot conduct electricity. This is spelled wrong. The behavior of these ions, both in the solid and in the liquid, tells us about how they function. And so ionic solids are stabilized by the lattice energy and the ionic bond formation, which is quite different than the covalent bonds we'll hear about in the next video.